Good afternoon, everyone, and thank you for joining us. We'll give the attendees here another minute or two before we officially get started. Good afternoon to everyone and those who may have just joined. We're right at about 1:00 p.m. Eastern time, which is our official start time. We'll give those signing in just another minute or two to get situated, and then we'll plan to officially kick off right at around 1:02 or 1:03. Thank you. So, good afternoon, everyone. We are a few minutes past our official start time of 1 p.m. Eastern time, and we'll go ahead and get started. So first of all, thank you for joining us today for our webinar on maximizing your productivity, hosted by MSC and Sandvik Coromant. My name is Chris Heideck, Category Strategy Manager with MSC, and I'll be kicking off today's webinar. This webinar features experts from Sandvik Coromant who will demonstrate how their tooling can help you maximize productivity, reduce your cost of ownership, and improve efficiency in your milling, drilling, and turning applications. The following experts bring extensive experience to today's call, from managing shop floors, to serving as process engineers, to providing technical expertise within their product focus areas. Leading us through today's webinar includes the following product specialists: Dan Tucker, over milling; John Winter, over turning; and Joe Hobbs, over drilling. Lastly, we are excited to share webinar participants will be entered into sweepstakes to win one of 3 $500 prizes, redeemable towards Sandvik Coromant product through MSC. We look forward to engaging with the winners and supporting their application needs. On behalf of MSC and Sandvik Coromant, thanks again for joining us today. I'll now turn it over to Dan Tucker with Sandvik Coromant.
Thank you, Chris. Appreciate that. So the first thing what we want to chat about real quickly before we dive into the product information is safety. Now, safety is the utmost importance for both MSC and Sandvik Coromant. So please, if you're not in a public setting, or if you're in a public setting, please understand where all the emergency exits are and assembly points, and of course, emergency number and protective equipment. Most important, or I'd say equally important, is psychological safety. Here we are really encourage you to ask as many questions as you feel relevant until we satisfy your answers here. Unfortunately, we're still in a COVID-19 situation. Some areas it's getting quite interesting, so we must continue to follow the local guidelines. Stay home if you're feeling sick, wash your hands carefully, and really most important is really observe your physical distancing. So hopefully someday we can stop showing this slide, but today we have to keep showing this slide. So the agenda today, I'm going to dive in first myself, like I was introduced, Dan Tucker. We're going to talk about the new core mill MH20. That's going to be effectively released October 1st of just a couple days down the road from here. Then after I get done, Martin Joe Hobbs is going to step in and he's going to talk about the 7x-D indexable drill, core drill DS20. And then John Winter is going to take us home with profitable steel turning with GC 4415 and 4425 for steel and prime turning. So let's dive right in. So basically, what is the core mill MH20? Why are we here talking about this today? So it's really a new high feed milling solution, and it's primarily designed for pocketing applications, and it's optimized first and foremost for super alloys and titanium. Stainless steel and steel is also a very good choice for this particular tool. As I said, it'll be introduced October 1st, and it's an addition to our high feed milling portfolio. This concept's good for all materials and all high feed milling operations. But like I said, it's significantly a productivity booster for ISO S and M, or it could be considered a problem solver. Now, why is that? Because it's got excellent stability and long overhangs. So this concept will be minimized to reduce your vibrations. As we all know, vibrations kill your tool life. The edge line is optimized for security in corner and pocket milling. We'll get into those details here in just a little bit. So this gives you the highest metal removal rate. What's really nice is a light cutting action ensures less power consumption. That's good for sustainable business, and that's really good for shops that got small machines. And this solution is reliable and secure enough to be ran in unmanned situations. And probably a real important, but not significant to some people from the naked eye, but this concept uses relatively large insert screws. So it's easy to handle, it's easy to index the inserts. Okay, so as we go through this slide, at the bottom is ISO P. So that's your steel materials like your 4140s, your 1018. And then you jump up into the middle where you got ISO M. This is your stainless steels, 316, 303. And then the top category is ISO S. This is your titaniums and your Inconels. So as you go up the scale on the Y axis, your machinability is reduced as you get up into the ISO M and ISO S materials. So you could easily say that in the top left-hand corner is optimized, to the right is economy, down to the bottom is economy, and then over on the far left is versatile. So you got pocket milling and corner machining on the left axis at the bottom left, and then you got shoulder milling and contouring, followed by face milling to the right. So today, we have very good products that cover face milling and shoulder milling along with contouring in ISO P, your steels, and ISO M in your stainless steels. They do function in the heat resistant super alloys, your ISO S materials, but they're not optimized for those products. So with the addition of core mill MH20 in both insert size 06 and 08, we now have a solution that focuses on optimizing in these areas. So let's talk a little bit about the application area. We've kind of touched a little bit on some of this, but in addition to corner machining and pocketing, we have ramping, helical ramping. It's really best in class as far as the ramp angles compared to the competitors out there. It'll do full slotting, also plunge milling, along with your regular shoulder milling and face milling. It's really good for both roughing and semi-finishing. This is not a finishing tool, although it'll leave a good enough finish that you can come back with a solid carbide and easily put a really nice finish on it. Here we're going to focus on aerospace frame. That's where we see a lot of the ISO S and ISO M materials, but oil and gas is equally important. But don't forget about die and mold, where we use a lot of ISO P and ISO H materials. Your ISO H is your hardened steels. Now remember, a lot of these parts, especially in aerospace frame and oil and gas, these are very expensive parts. So the reliability and security of the MH20 gives operators and owners a peace of mind. So the assortment overview, as you see it on the screen, we're basically going to cover a 5/8 to 1.5 inch. Today, we're going to have 7 grades and 3 geometries. Tomorrow, what I mean by tomorrow is we're hoping before the second quarter of 2022, we'll also have up to 2-inch diameter available and some new grades and geometries for a little bit tougher ISO S, ISO M insert. So there's more to come on this product, but this is what we're releasing in October. So let's talk about the cutter body a little bit. What's new about this? I think the most pronounced and improvement that we can show here is it's a new cutter body material. We already offer our milling products in an industry-leading Coromill steel body. And what that means is it comes pre-heat treated. What this new material is showing is up to 7 times, and we've already seen up to 10 times better fatigue resistance, meaning it stays in the cut longer, the insert pockets last longer. It's a tougher material than we use in our other Coromill products. Also, the pocket where the insert's mounted has been optimized for high feed milling applications. The chips that come off of there take a really kind of unique pocket for them to get out of there in the right way. Yeah, of course, we got the internal coolant and a shank that you can cut to your desired length. Let's take a look at the insert here. I want to bring a couple things to your attention here that are really important. The far right-hand side, I guess, far right-hand side of the insert, shown in light blue, it's a reinforced insert corner. And so when you're pocketing, you have a lot of challenges, and these challenges can be addressed in a lot of different ways. But like I said, let me bring your attention to that area. It's got a curved and reinforced corner for strength and clearance. So this will give you the predictability that you need, and it'll allow the chips to get out of there without them being trapped. So it's got some clearance built into it, and it allows the finish of the material, which we'll show here in a little bit, the part or the feature that you're machining looks a lot cleaner. The other thing I want to bring to your attention is down at the bottom, you'll see a flat. And this flat on the insert is it's a very stable axial support area to when you're doing helical ramping or circular ramping, the insert is very stable in the pockets, being reinforced. And that gives you a lot of predictability as well. And we're going to talk about the top left comment here about prominent marking for differential geometries. We're going to talk about that in a slide or two in a few minutes here. So a lot of unique things going on with this geometry of insert. Now the question is going to come up, why did we introduce a 2-cornered solution, which the MH20 is, versus a lot of competitors that have 4 and 6 corners? And it's a legitimate question. Process security and optimization for ISO S and M material is the main reason. Here we have a little bit more freedom to design an insert that is optimized for those types of materials. The other thing is, as you can see on the screen with this kind of a red circle that's, I don't know, kind of got some spacing in. I'm not sure what the right terminology is there. It's not a complete circle, but you can see on the 2-edge solution, It's all blue on the screen there. Now what you're looking at here is a heat situation. So the warmer the colors, the hotter that you're seeing on the edge line. And where the insert is the weakest on this 2-edge solution is where you have the least amount of heat. So the cross section is not seeing any stresses and it's not seeing any heat. So it's very stable and very strong. Whereas a 4-corner solution on the right-hand side, where you see all the heat and all the pressure, it's at the weakest section of the corner, or the weakest section of the insert, I should say. So it's a much more stable insert, it's a stronger insert, and that's why we went with the 2-edge solution. As I indicated earlier, we have markers on the insert. On the very top, you'll see that red circle again, going from left to right. The EL30 geometry is an optimized peripheral ground geometry for your stainless steels and your titaniums and Inconel. It's very light cutting. Like I said, it's optimized for those materials. And that marker on your insert straight up. As you move to the central insert, this is direct press geometry, and it's the M20. This is more designated as your first choice for your steel and hardened steel applications. Still light cutting, but a little bit more stable, a little bit stronger. Very versatile geometry. All the way to the right, you can see the M50. And this is also direct press geometry, but it's more negative, it's stronger. It's, maybe for your interruptions or less stable situations. Here, you can also get a little bit more feed rate out of the insert. So it might be a productivity booster for you. Just some basics about the concept. It is a 15-degree lead angle. The maximum depth of cut for the 06 insert is 31 thou, and for the 08, it's 51 thou. For this type of concept, programmers want to know what the programming radius is. So in the product code or the insert, you'll see for the 6 insert, it's going to be a 79 thou or 2.0. And for the 8, it's a 2.5 millimeter or 98 thou programming radius. Again, this is information programmers need when they implement this tool. Now here's a test that we did comparing against our own Coromant 415. And this was in titanium. It was for wing support on an aerospace part. You can see the machine details up there. I'd like to draw your attention to the pictures on the right. As you can see, after 49 minutes with our existing insert, we're getting some pretty good banged up cutting edge conditions there, some adhesion leading to inserts chipping. And that's after 49 minutes, whereas you compare it to the MH20, almost 65 minutes, and it had more to go. The edge line looks pretty pristine. It looks very nice. And then pictures are worth a million words. As you look at the finish now, comparing the 415 to the MH20, you can see the 415's got a lot of vibration, a lot of chatter, and there's material sticking to the finish there, impregnating in the wall. Whereas MH20 is very clean. So when you come back in with a solid carbide tool or a replaceable tip carbide tool, it's going to be a lot easier to do a cleanup pass on this material. Overall, this customer would see a 32% increase in tool life. And this customer actually told us that that he would definitely implement this tool just because of the process security and the stability and the tool life he sees here. One more little performance test. This is against a competitor. And this is more like a 4140 material. So like I said earlier, it works very well in ISOP materials. And here we ran a little bit greater productivity, a little bit faster surface footage, but I want to bring your attention to the tool life here. The competitor also had a lot of time in cut as well. But both these tools were in the cut a long time, but you can see the competitor's tool is in pretty bad shape. And I think you can continue running the Coromant MH20 insert. Pretty impressive results. Okay, so we will now transition over to my compadre here, Martin Joseph Hobbs. Joe, the floor is yours.
Thank you very much, Dan. As was mentioned, I am Martin Joseph Hobbs. I am the drilling product specialist for the Sandvik Coromant. And today we're going to be talking about the core drill DS20. And the DS20 was released in the fall of 2019. and is the first drill capable of reaching as an insert drill to 7 times diameter. It ranges from 15 millimeter to 65 millimeter in diameter and comes with 2 different shanks, the ISO 9766, which is the cylindrical with flat, as well as the MDI connection. The MDI connection then also has 2 different shanks available, HSK, as well as Sandvik Coromant's Capto connection. I want to focus a little bit of time on the design of the drill and the design of the inserts, because it is very important for us to understand the differences between the new DS20 technology and the older technology. And we'll compare it to our core drill 880, but almost all insert drills fall into that same category. As you can see with the central insert, we have 4 corners on the top edge. And with the peripheral insert, we have 2 on the top and 2 additional cutting edges on the bottom. And for that reason, we have to tip the insert at a negative angle in order to protect the back cutting edges while it is drilling. This is also designed to keep us deflecting the cutting forces the direction that we need them. And we'll talk about that shortly. To help understand which corners are in cut, you can see we have corner indicators, the 1 dot, the 2 dot, or the 3 dot on the copper colored insert for the central. And then if you look at the black and gold insert to the right, you can see we have 3 dots facing the drill, 4 dots facing away. And then on the gray, you can see the 1 and 2 dots there. We can line these insert dots up and always know which cutting edges have been used or not used. So here's the cross section I was talking about, where we compare the core drill 880 to the core drill DS20. As you can see with the 880, it had a 5-degree positive rake angle, and now we're going to a 5.3 to 5.4 negative rake angle. This is designed again to balance cutting forces as well as give us the protection we need on the non-cutting edge of the insert. So we're going to take a look at our inserts here. Again, you can see now those dots very prominent with the front of the insert here, where you're capable of seeing corners 1, 2, 3, and 4 being able to be used. And you'll see we have 3 different grades. The 1344 grade is going to be the most common grade used in almost all applications. So if you have a job shop that runs a large different batch of materials, 1344 is going to be the insert that you want to use. Now, if you want to optimize your setups and you need to go with a stainless or a heat resistant super alloy grade, that's when we're going to want to run the 1144. And then for our non-ferrous materials, we have the H13A. The L5 and the M7. The biggest thing to know about these is that the M7 is for your short chipping materials, especially in your cast irons, where the L5 is for your longer chipping materials. And it's the easiest way to remember it, L for the longer chipping materials. So let's take a look at the peripheral insert grades and talk a little bit about those grades now. We still have the same grades available to us that we had with our core drill 880, where we have the 4344, which is a very tough, robust grade capable of taking a lot of abuse. 4334 grade, which is designed for our average materials, and in most cases will be the grade that we will run. And then we have the 4324 for our very stable conditions. And when I talk stable, we don't want any intermittent cuts. We don't want any interruptions. We don't want a lot of vibrations. So then for the stainless and our heat resistant super alloys, we're going to have the 2044 grade, as well as for our non-ferrous, the H13A at the very end. With these come 5 chip breakers, and these chip breakers are slightly different than the core drill 880. So we're going to talk about the nomenclature we use to talk about them. The S, the L, the M, and the H refers to the sharp cutting edge, light cutting edge, medium cutting edge, and a heavy cutting edge. So that's how we want to think about them. S is going to be for our, say, our non-ferrous materials, some heat resistant super alloys. Our L5, now that 5 is going to be a medium edge prep, where the 6 is a little bit heavier edge prep, 7 even heavier edge prep than the 6. So that light edge prep is going to be used in our long chipping materials, such as our 1018s, 8620s, and our L6W is going to be utilized more in applications where we have harder materials or even some very aggressive abrasive type materials. And that M7 is going to be used in our short chipping materials again. And the H5W can be used as a complementary grade for our longer chipping, but it's also going to give us a negative T-land for better tool life. And that negative T-land gives us a very heavy honed front edge on that insert. So when we think about these, the S5, L5, L6, M7, and H5 are the order that they go from sharpest to heaviest cutting edges. And then along with this, you see the W, and the W stands for the wiper, which is on the peripheral edge of the outside corner, which helps to give us a much better surface finish going down through the holes as we're drilling. Now, the drill body itself, we see 2 different distinct chip flutes here. The central chip flute, which is on the left in this particular picture, is deeper than the peripheral chip flute or the outside insert chip flute. It's also more narrow, and that's to fit the chip that goes through that drill body. So we've now tailored the drill body to handle the exact chip that comes through it. And that's why you see the right-hand side of the chip flute there being a more kind of open-topped, shallower chip flute. That allows for the 6s and the 9s to escape the chip flutes better. These 2 different chip flute shapes also help us break up the harmonics that the drill produces when it's drilling at deeper lengths, giving us better stability. And we put the 2 coolant holes on the outside of the drill body, giving us a thicker web and better stability while drilling. And this is the reason why. When we look at this chart on the right-hand side, where it has drill length at the bottom in 2 to 7 times, and the deflective cutting ratio that you see on the left-hand corner, this chart shows you how many more deflective cutting forces we see when we go from a 2 times to 7 times drilling application. And we get to start seeing us ramp up to 40 times more deflective cutting forces. That is why we had to change the design of the drill as well as the insert to handle those deflective cutting forces to keep our drill running straight and true. One of the unique features of this dog bone shaped insert in the peripheral pocket is now on a lathe application. When we're drilling a through hole, we're capable of coming in and removing the burr on the back side of the through hole. This is very advantageous to burr-free machining that we often ask for when we're drilling holes and or milling edges. This drill allows us to do that application. However, there is some math involved with it. So get with your local Sandvik Coromant team to help you with that math and understand the direction we have to go in order to produce this burr removal situation. As I indicated earlier, we released the new modular drilling interface, or what we call the MDI. And this MDI connection comes in Coromant Capto as well as HSK connections. It has 4 pins in the face of the adapter that locates on the 4 pinholes in the backside of the drill. The backside of the drill and the inside connection of the holder are both ground to tight tolerance for the most snug fit. And we have a quick animation to show you how these drill holders and the drills work together. As you can see in this demonstration, the drill can be rotated 180 degrees, but it cannot be rotated 90 degrees because of the alignment of the pins. This really helps when putting this drill in a lathe application to prevent people misaligning the tool. So now I want to go over 3 quick success cases where this drill really stands out. The first one in a standard 4140 in a slewing ring. And if we look at this slewing ring, you can see the holes in the outer peripheral of the ring where we were drilling. This drill was run against the core drill 880 4x D drill, and now we're running a DS20 5 times. Because of the application with the DS20, we were able to increase our surface footage, increase our feed rate, and reduce the cycle time, producing an increased productivity. And you can see that in the chart to the right there with the little bubbles. The tool life in pieces remained the same. That's significant. We still were able to get 4 complete pieces while increasing productivity. In this particular case, we see a titanium rod that we had to drill a hole through. And you can see in the picture how clean the hole looks and how nice that surface finish is as it goes through this drilling application with a 7 times diameter drill. This drill was run with the S5W 4344 grade and an L5 central with a 1344. We were able to drill this complete holding size and tolerance for this customer, giving him an application to remove the spade drills that they were running in there, reducing their tooling costs and increasing their productivity. This is an application that I ran into, and this challenge was significant because we had to enter and exit at 52 degrees. On the entry side, it was simple enough because we were able to run a helical circular motion to mill out the flat for the drill to enter on. However, as we exit the back of the material, we had to exit at 52 degrees. This drill, because of its rigidity, was able to do this when other spade drills, solid carbides, and insert drills were failing. The DS20 was capable of drilling this hole out. And because of the unique nature of that dog bone peripheral insert, not only were we able to drill through the hole, but we were able to slow our feed rate back through the interruption, helping to take some of the deflection that was created out of the hole, giving the customer the truest, straightest hole possible. And with this, at this time, I'd like to turn it over to John Winter, our turning specialist.
Thanks, Joe. That was great. So I'm going to talk to you a little bit about some grades for steel turning. We've seen milling concepts, and Dan talked about the proper grade selection depending on the material. Joe did the same thing with the DS20. And here we're going to actually focus just on grades for steel turning in the next generation in Veo coating. This coating gives us the technology to align the crystal structure to give us the hardest possible coating on the insert to give us the best possible tool life. We have brand new substrates, which are unique with good combination of toughness and resistance to plastic deformation, offering reliable performance. We also have a new post-treatment process, which actually hardens the aluminum oxide to give us an even harder, consistent coating on the top of the insert. With these combinations, we are seeing an average tool life gain of 25% just by dropping these into the pocket where you're turning any kind of steel applications. So the application area is going to be automotive components, heavy trucks, heavy vehicles, regular cars, construction equipment, railway turning, general engineering, anywhere you're running low and unalloyed steels, both internal, external, from finishing to roughing and everything in between with continuous and light interruptions. So here's the positioning when you look at the whole steel turning offer. So you look at 4305, this is a grade that's designed for long continuous cuts in stable conditions with no interruptions and no vibrations. 4415 can handle some of that, but also can handle a little bit of vibration or instability and gives you the same consistent tool life. 4425 is going to be the grade that you're going to want to start with. And this can handle minor interruptions like small little cross holes or scale or in and out of cut from a forging. And then anywhere you're cutting really heavy interruptions, say across the keyway or spline, that's where you're going to look at the 4335 grade. So here's how we refine the 4415 and the 4425 versus our old 4315 and 4325. So in this illustration here, you can see the crater and flank wear resistance. We've improved that dramatically, along with improvements over plastic deformation. And then in edge line security, we've gained a little bit in the 4415, but we've had great gains with 4425. And again, this gives us roughly a 25% improvement in all application areas and gaining that tool life. The best illustration is looking at a wore out insert. So in this illustration here, you can see the first generation Inveo coating. That's the top graphic. All these inserts ran the same cutting data and the same amount of cut time. So when you look at the lower one, the next generation Inveo or the 44 series grades, you can see that edgeline security and resistance to plastic deformation is key. These grades work extremely well and can gain you that 25% improvement in tool life just by dropping it in. Here's a great success case against a competitor. You can see here that we're able to optimize. These grades can handle a little more heat, so we actually ran it a little bit faster. We picked up the feed rate a little bit, so here's your productivity gain by plugging these in. So if you have the time to dial these in, they can be a great gain in productivity. And yes, we also still doubled our tool life. Went from 40 pieces to 80 pieces. Both tools wore out and gave us a bad surface finish. That's why we had to change them, but doubling the tool life and also gaining that productivity gain was instrumental in the win. Here's another great success case. And I talked about just dropping it in and gaining about 25% improvement in tool life. Here we ran against a competitor. Again, dropped it in, didn't make any adjustments, and went from 10 pieces to 24 pieces. It's a little more than that 24% improvement that I was talking about. So now how do you couple those new grades with a major productivity booster in prime turning? We're going to take a look here. But first of all, what is prime turning? So prime turning is the methodology of using one tool turning multiple directions. That's what the graphic shows here. The orange arrows would represent a high feed direction or chip thinning, and then the yellow dashed lines would actually represent conventional turning or turning in the conventional direction. The tools to do that are core turn prime turning tools. And then we also have software available to help you reprocess your parts to give you the proper tool path for the prime turning. So the Cora Plus tool path for prime turning software will generate just the code needed for that tool path for the prime turning. You will cut and paste and put it into your existing program and you're off and running. So here's a little better view of the tools. We have an A tool, which is for light roughing, finishing, and profiling. This is similar to a VNMG or a DNMG style tool. And we'll be able to use the high feed and also come back and do profiling and finishing with the front of the tool. The Prime B it has an 80-degree nose on the front, similar to a CNMG or WNMG style insert. And it is for roughing, but in the conventional direction, you can also finish with the tool. These tools can be used for external and internal machining. We have tools available to do both. And we also have the grades available to run in all materials. So what's really the difference? Prime turning takes advantage of a lead angle. So here you can see conventional turning versus prime turning. And what's in blue would be where we're feeding, our feed rate. So in a CNMG insert, if you're feeding at 5 thousandths of rev, that chip thickness is going to be roughly 5 thousandths of rev. If you're feeding in the prime direction using Prime B at 5 thousandths of rev, that chip thickness is going to be a little bit thinner. So you need to maintain a certain chip thickness, thus allowing us to increase the feed rate. This also takes the heat away from the cutting edge. It spreads it out more versus all that heat on the front of the insert. Here's a better illustration. So if we want to maintain the same chip thickness for either a CNMG versus prime, these are the equations available in order to do that. Same with the VNMG insert versus the Prime A insert. But we need to maintain a certain chip thickness. The insert's designed to see that thickness of chip. That's why you have to pick up your feed rate in order to maintain that. So here's a good illustration. So say you have a CNMG insert and we want to maintain a 0.4 millimeter chip thickness. So you can see here we have to feed at 0.4 millimeter when you're running a CNMG insert. When you look at Prime B, to maintain that 0.4 millimeter chip thickness, we will actually feed the tool at 0.95 millimeter of rev. That's basically 138% improvement in productivity. So how does that chip thickness and hex influence our feed rate if we're doing any kind of profiling? This illustration here shows that in the yellow, we have our feed rate and the high direction. But when we open up that lead angle to come down an angle, we need to slow that feed rate down. We don't want to overload the insert. But when we come back to that tangency point, we can pick the feed rate back up. Now, if you're going to come up an angle and you close that lead angle, now you can increase that feed rate even more. And then when you come back to that tangency point, maintain that same feed rate in the yellow to maintain the productivity gains for the tool. So using that in mind, here's an illustration of machining a part. We're actually going to start with the yellow in the high feed direction. We're going to hit the face of the tool and feed down in the conventional direction. That's why it's a white dashed line. Then we get down to the shoulder corner. We're going to pick up our feed rate until we hit that upward angle. We're going to feed a little harder, come towards the end of the part, and then we'll conventionally turn down the face of the part. So here we're using basically one high feed edge and the nose of the insert. But what if we think a little bit differently in how we're going to apply this tool? What if we look at this illustration here and you high feed on the flange, and you come down into that corner and you roll in and high feed up the flange. So now you use two different edges of that insert, come back down to that corner, roll in and high feed on the barrel, come up the angle, high feed to the end. Now, if your machine has the capability of changing spindle direction and moving past center, then you can actually high feed from center in. If your machine does not have that ability, you're going to have to conventionally turn to center, or there's a minimum diameter that you can roll in and high feed out, but you're still going to have to use conventional turning to finish the part. But by doing this, we've changed the wear characteristics on that insert. So what we've done is you've taken a conventional insert, we put all the wear on the front of the tool. It doesn't matter if you're longitudinal or if you're facing, all that heat and wear go to the nose of the insert. Whereas with prime turning, we're changing back and forth. We're feeding on the longitudinal side on one edge, we're feeding up the face on the other edge, spreading that wear out, spreading that heat out. And then I can come back and finish with the front of the tool and do some profiling. These are great ways to gain productivity and tool life by managing your edges. I've got 3 edges on one corner of the insert by using prime turning. Here's a great illustration of that. So we ran some 316L stainless steel. Granted, we ran grade 2025, which is a steel turning grade for prime turning. Here's the cutting data. And you can see the tool life in the top, 18 minutes versus 100 minutes. So when you look here at the conventional wear, we're putting all that heat on the nose of the insert. You can see a little bit of cratering starting. You can see some notch wear at the depth of cut. And the insert looks pretty wore out after 18 minutes. Whereas with prime turning, we've taken all that heat, spread it out, we spread that lead angle out, and we ran 100 minutes of cut time, and that edge looks virtually brand new. Here you can see the edge line with the plastic deformation. So you can see the nose of the insert saw a lot of heat. We got a little dip in that edge line, which tells me we got some plastic deformation. Whereas the prime turning, we still have no wear on that edge. We could actually go a little bit longer if we had more material. So now how do we couple that with the new grades? So here's a great illustration where we were running prime turning with the 4325 grade. So we didn't change anything but put the grade in. And I talked about, a 20%, 25% improvement in tool life with the new grades. Here in this illustration, we had a 90% improvement in tool life just by dropping it in. So here our customer gained the productivity gains by putting prime turning in, and now also gain the tool life gains with the new grade. So you can see in the what I call the spider graph off the side, the 4325 grade in the maroon color, we set that all as equal. And then you look at the orange line, these are the areas that we've increased improvement of the 4425 grade. Flank wear, crater wear, toughness, edge line security, and edge line depression. Now, edge line impression, it's pretty close to the same, but we had a little bit of improvement there also. Now, there's some important things to remember when you're applying prime turning tools. You do need to roll into the material. You can't plunge straight down. You will damage the cutting edge or the nose of the insert. So you make sure that you're rolling in, and the prime turning code generator will actually generate that radius for you. Same thing if you're doing ID turning, and that reduce feed through that radius. Then once you hit that tangentially point, you can pick up to the high feed. Now, I mentioned programming. There are several softwares out there that embed prime turning into their software. MasterCam and Siemens NX both have prime turning modules in their system. So if you're up to date on those, you should have that available. And then Core Plus Toolpath is actually a license where you basically pay once a year for the maintenance fee. And then as we upgrade and add things, you will always be on the latest. So with that, I'm going to turn it back over to some questions. And from what I can see here, I'm not seeing any questions at this point in time. I do notice that in the chat function, Alex has uploaded a couple videos. So we have some videos that you can watch when it comes to the grades and the DS20. So there's some great videos there to watch. And then keep an eye out after October 1st for the MH20. It's a great new high feed concept that is going to do some wonders when you're trying to do some pocketing, especially in heat resistant super alloys. So with that, I'll turn it back over to MSC.
Thank you, John. Again, this is Chris Heideck with MSC. As we start to wrap up today's session, bear with me just a moment. I did notice it looks like one additional question came in. And let's see. So John, maybe I will pose this question to you, but feel free to get others involved if needed. But one of our participants had asked, what is the lightest depth of cut for prime turn in a finishing type cut?
Well, with the finishing application with the prime, you really need to look at the whole stability because it will put some tool pressure in. But you can do, you know, an 8,000 depth of cut from a finishing application standpoint. But keep in mind, as you do that high feed, the lighter the cut, you're going to want to probably ride up. So I would actually need a little more material when I'm finishing in the prime direction. If you rough in the prime direction and finish in the conventional direction using the same tool, it runs just like a VNMG style tool. So the depth of cut is based off the nose radius.
Very good. Thank you very much, John. We had another question come in. What is the Zertiv's coating, for example, GC 4344?
Or the Zertivo coating. So the Zertivo coating is basically, it's a bonding process. It's the way the coating bonds to the substrate. In some cases, you can get some flaking when you look at the PVD coatings, and it's very important that you have a very secure bond. And the technology for Zertivo is that bonding of the coating to the substrate. We don't get any flaking or any issues, and we have a very strong bond.
And I think Alex can share a link at some point to the audience to learn more about Zertivo, the technology, from our website.
Thank you very much, John, for the feedback and for the recognition of that correction there. Thank you. Maybe just open it up once more to the audience. Any additional questions before we start to close? Great. Well, thank you so much for your feedback there. And again, just to officially wrap up, as a follow-up to today's session, we will be sharing a copy of the presentation today, as well as additional resources on the solutions that the Sandvik team spoke to this afternoon. We'll also include information on contact information if you have any additional comments or questions. So with that, to the Sandvik team, thank you so much for your time this afternoon and your expertise. And to the audience, thank you for attending today's webinar. We will go ahead and conclude the call. Thank you.
Thank you, Chris.